Hello, welcome to another talk. This time we're going to look at the Hubble constant. We're going to clarify the importance of the Hubble constant, also called the Hubble parameter. Why is it so important? How does it relate to the age of the universe? Has it always taken the same values? And if not, how does it impact the calculated age of the universe? Here we have a diagram showing the theory of the Big Bang. On the top we have the creation of all the particles, quarks and leptons, nucleons, nuclei, atoms, stars and galaxies. So going to increased sophistication on that way. The time increasing from here, 10 to the minus 44 seconds, which is otherwise known as the Planck time, all the way down to 100 seconds, 1,000 seconds, 300,000 years and today. The temperature being really hot, 10 to 32 Kelvin, all the way to 3000 Kelvin and 3 Kelvin, and then energy going from giga electron volts, a massive amount of energy, to kilo electron volts to the 10 to minus 3 electron volts today. And then we have these appearances of the end of grand unification, the end of electroweak unification, primordial nucleosynthesis, and the last scatter of the background radiation. This is a schematic again of the age of the universe from t equals 0 until today. Low energy to high energy. We start off with the four forces we have today: electromagnetic interaction, weak interaction, strong, both nuclear, and the gravitational interaction. That theorized as the energy goes up massively and the time shortens towards the beginning of the universe. Then you have 10 to the minus 12 seconds, you have electroweak interaction, which is the merging of electromagnetism and the weak nuclear force. 10 to the minus 36, you have the grand unified theory of the electroweak merging with the strong. And at the Planck time, the theory of everything, we have all four forces theorized to be united in one. How do you measure the observable universe? Well, one approach is to take the sun as the bottom of a triangle and the Earth as one side, and then measure the distance here, which is one astronomical unit, an AU, and that is 1.50 times 10 to the 11 meters. Now the parsec is this huge number here, which is 10 to the 5 times bigger. So the arcsec is exaggerated because this angle here is about 10 degrees. It needs to be divided by 10 and then divided by 3,600. So you need to make that angle so small that that length here is going to be really long, because the star is going to be right off the page to make that angle, because an arc second is 1/60th of a minute, which is 1/60th of a degree. And that's the size of a parsec. We don't use light years in astrophysics. Parsec is a big enough unit that we can use. The next video talks about doing a Kessel run in 12 parsecs.
Fast ship. You've never heard of the Millennium Falcon?
Should I have?
It's a ship that made the Kessel run in less than 12 parsecs.
Okay, on the scale of the universe, as we have laid out here, the Milky Way galaxy is 40 kiloparsecs across the Milky Way galaxy here, and the Andromeda galaxy is measured to be 660 kiloparsecs away, which then goes to the local group of galaxies, which is 100 megaparsecs to the Coma cluster of galaxies. So with this data given, these are the scales. So 40 kiloparsecs ends up being 10 to 21 meters. 660 kiloparsecs is 10 to the 22 meters, and 100 megaparsecs is 10 to the 24 meters. What about the value of Hubble constant? Well, you'll see from 1920 until the year 2000 that the Hubble constant in terms of the units of kilometers per second per megaparsec. Here we have kilometers per second per megaparsec, really unusual units. That's a value today. But you'll see in the past it's taken ranges of values with these uncertainty bars. Anything, this was a huge uncertainty bar there, anything from 605 all the way down here to, in the last 20 years of the last century, being round about 70, up and down here. On the right we have a list of data given of the different value measurements over these years. Quite handy to have a look at those values. Okay, now we're going to use the Hubble constant and see what we get out of it. So we're given that h naught equals 72 kilometers per second per megaparsec. Changing the units very carefully, we have 72 times 10 to the 3 meters per second. Per megaparsec, parsec goes on the bottom, mega is 10 to the 6. Changing this one carefully to 7.2 times 10 to the 4 meters per second. We have parsec, and then we're changing the parsec into meters, so multiplied by 3.09 times 10 to the 16. Then we have that measured, that value worked out. Line by line calculation, the units cancel, we end up with 2.33 times 10 to minus 18 per second. Now if we take the reciprocal, which means we turn it upside down, we have a second on the bottom, per second on the bottom here, and as we flip it we get a value of 4.29 times 10 to 17 seconds. If we then divide by how many seconds are in a year, 60 seconds in a minute, in an hour, in a day, in a year, and days in a year, and then we end up with 1.36 times 10 to the 10 years, which is the age of the universe as theorized with these values, giving a value of 13.6 billion years. The values that you looked at before in the table in the actual graph, I've gone for the maximum value. If you have the maximum value on a spreadsheet here, 600 kilometers per second per megaparsec, and calculating all the way through, we end up with the age of the universe, the minimum age. So maximum value of Hubble constant gives of 600 kilometers per second per megaparsec, gives a minimum value of time of 1.63 billion years. The minimum value of Hubble constant 50, doing the calculations, ends up as a maximum value of 19.58 billion years. So from this data, we can see that the universe has been theorized to be anything between 1.63 and 19.58 billion years old. Thanks to S104, S217, S282, the YouTube video on the Kessel run, and the Hubble data.